Okay. Okay, so I guess we can start. We are all here. So first of all, thank you everyone. So I'm Ferrano Gelaguet. I will be chairing the session 8 about redirection and locomotion. So today we have 6 really interesting papers about redirected walking and assisted locomotion in real and virtual environments. So first, before starting, I have several announcements from Ismar, and also you will, after we are the second day, so you will we will refresh all the things. So first of all, remember that that there are individual Discord channels for each of the papers. So if you have questions, you can use these ones, or you use directly the Q&A feature from Zoom. And also at the end of the session, you will be able to join all the speakers in the Q&A sessions in GatherTown. So please go there if you have to discuss with the authors when the session is finished. And also for all the people watching us from YouTube, remember that you can register to Ismar if they want to have access to the GatherTown and the Zoom links. So our first presentation will be given by Yijun Li, who is a PhD student from the Beihai University in China. So Yijun, I think that okay. So you can start.
Okay, how about my slides?
So they are loading.
Okay.
Yeah, everything is good. So go ahead.
Hello everyone, I'm Yijun Li from Beihai University. Today I'll introduce our paper, OpenRDW, a redirected working library and benchmark with multi-user learning-based functionalities and state-of-the-art algorithms. Nowadays, with the increasing popularity of virtual reality applications, more people are willing to experience VR in room-scale spaces. When experiencing this immersive exploration, free movements in virtual environments are essential. However, traveling in the large virtual space can be highly constrained by the limited physical tracking space. Therefore, some effective locomotion techniques such as teleportation, walking in place, and redirected working were proposed to offer a better VR experience. Among these techniques, RDW can provide a high natural feeling of walking by introducing imperceptible manipulations to guide the user away from the physical boundaries, which enables users to explore a larger virtual space. For example, when a user plans to walk along a straight path in the virtual environment, the virtual camera could be slightly rotated so that the user unknowingly compensates this rotation by walking along an arc in the real world. This virtual rotation speed is usually controlled by parameters called gains. A taxonomy of redirection involves 3 major gains, namely translation, rotation, and curvature gains. To mimic the natural working process in the real world, the gains should be constrained within certain detection thresholds measured by user studies. Redirection controllers are specific algorithms which determine how gains are applied to steer users. Subtle redirection controllers steer users imperceptibly, including steer-to-center controllers based on artificial potential fields or reinforcement learning. But sometimes it is still possible for users to reach physical boundaries, which should be corrected by overt redirection controllers like Toolkit. To reduce the complexity of deploying RDW for VR developers, software libraries such as the Redirected Working Toolkit were developed to offer basic program interfaces for algorithm design, working simulation, and data logging. But till now, there are still very few released open source RDW platforms, and more new features can be supplemented to handle complex applications.
Okay, that he will come back. Yijun, do you hear us? Okay.
Yijun.
Let's wait a couple of minutes. I think he froze, so
Okay.
this is the problem of doing that in direct.
Yeah.
Wait just 1 minute to see if he can come back. If not, we can switch to the second presenter.
Oh.
Okay. So. So I think he's talking, but
Yeah.
we don't hear him.
Yes, the same here.
Mm.
We cannot hear, and but the slides is still.
Yeah.
Okay.
It's strange. Yeah, same here. But I mean,
Yeah.
I think it's really strange because the slides are. I thought he froze and he was disconnected, but no, he's still connected.
Yeah, the slides is still moving, but his image stopped.
There is a way to start the sharing, so he might realize that it's not working.
Yeah, I sent him a message, but no.
Okay, so can someone?
Yeah.
Okay.
Okay.
So well, in this case, I propose that we switch to the second presenter and we'll see if we can catch up after with this presentation. So Hiroaki, are you there? Are you available? Are you ready?
Okay, I'm here.
Okay, so please we will go to the second presentation. So please share your slides.
Okay.
And we will do the next one once Yijun is connected. Okay, so sorry for these technical details, the technical issues. I hope that it won't be always the case. So we will go to the second paper, which will be presented by Hiroaki Sakono from the University of Tokyo. So, so please, Hiroaki, you can.
Yes.
Your slides are okay. So go ahead, please.
Okay, can I start now? Okay.
Yes, go ahead, please.
Okay. Hi, I'm Hiroaki Sakono. I'm going to give a presentation on this research, redirected walking with continuous curvature manipulation. The four authors of this paper are shown here. First, we describe the overview of our study. We propose a novel redirected walking technique that applies dynamic bending and curvature gains so that users perceive less discomfort than existing techniques with constant gains. The person in this video walks along a path whose curvature is gradually changed in the virtual environment while it's fixed in the real environment. With the development of VR technology, various methods for walking in virtual environment have been devised. While the technology to walk in a large space by simply performing walking movements on the spot using special equipment has been devised, there's a need to realize a highly immersive walking experience that is closer to the actual walking sensation. To meet this need, a method called redirected walking has been proposed. In this method, the visual information that the user sees through the HMD can be slightly manipulated to make them perceive that they are walking along a different path than the actual one. Manipulation methods for redirected walking includes translation gain, which manipulates the distance the users move, rotation gain, which manipulates the amount of rotation, and the curvature gain, which manipulates the curvature of the path. However, there is a limitation to these manipulation methods. The limitation is that there is a very limited range of gain that can be applied without the user noticing. For example, when applying curvature gain, if the radius of the real path is 22 meters, the user will not notice the manipulation. But if the radius is 5 meters, the user will notice the manipulation and it will cause a great deal of discomfort. To expand the range of applicable gains, there is a method that uses dynamically varying gains. This study compares the case where the gain is increased discretely, as shown on the left, and the case where the gain is increased continuously, as shown on the right. It is shown that the latter case is more difficult for the user to notice the manipulation. Based on these backgrounds, the objective of the study is to explore a more versatile and effective RDW methods that take advantage of dynamic gains. In this study, we focus on the curvature manipulation and verify the effect of suppressing the discomfort perceived by the user by utilizing dynamic gain. In this study, we apply dynamic gain in curvature manipulation by continuously varying the curvature of the user's walking path. To apply dynamic gain, we utilize a closed curve for the user's walking path. The curvature of the curve varies in proportion to the arc length, and this curve is used in curves of highway and vertical loops of roller coasters. By using this curve, the curvature of the path can be changed continuously and dynamic gain can be applied. The curvature manipulation in this study targets two types of gains. One is bending gain, which manipulates the curvature of the path in the VE and is defined as the ratio of the radii in RE and VE. The other is curvature gain, which manipulates the curvature of the path in RE and makes the users perceive that they are walking on a straight line in VE and is defined by the curvature in RE. So we describe a method of applying these gains in a dynamically changing manner. First, let us describe dynamic bending gain. Dynamic bending gain can be achieved by manipulating the user's viewpoint from a circular arc having constant curvature to a closed curve having dynamic varying curvature. Second, let us describe the dynamic curvature gain. Dynamic curvature gain can be achieved by manipulating the user's viewpoint from a closed curve with dynamically changing curvature to a straight line. We conducted two types of experiments based on the proposed method. The first is to investigate the relationship between the curvature change rate and the user's perceived discomfort. The experiment was conducted for bending gain and curvature gain, respectively. The second is to verify the effect of suppressing the user's discomfort by selecting an appropriate curvature change rate based on the results of the first experiment and applying a dynamic gain that utilizes continuous curvature change. The experiment were conducted for bending gain and curvature gain, respectively. Due to time constraints, we will focus on the experiment 4 for curvature gain in this presentation. In this experiment, we examine whether the discomfort perceived by users can be reduced by applying a dynamic curvature gain with continuous curvature change. The effect is verified by comparing the case where the curvature gain is increased continuously, like a ramp function, and the case where the gain is increased discretely, like a step function. This is the scene of the participants in the experiment while walking. We created the virtual environment by Unity, and this consists of lawns, trees, and huts. Participants walked 20 meters while changing direction every 5 meters in each trial. In other words, the participant changes direction 3 times in each trial. At the end of each trial, the participants answered a questionnaire about the discomfort they perceived. So about experimental design, a total of 18 participants participated in this experiment, and 2 conditions were set for the way of curvature change, and 2 conditions for the maximum curvature gain per each trial was set, and a total of 4 conditions were set by combining them. So about details of each trial, and after walking 20 meters in each trial, participants answer the magnitude of discomfort during walking using a visual analog scale from 0 to 100. The experiment was conducted for 16 trials in total. The 2 conditions for the way the curvature changes are shown here. One is the continuous condition, in which the curvature increases like a ramp function by applying a dynamic curvature gain, as shown in the left figure. The other is the abrupt condition, where the curvature increases like a step function by using a constant curvature gain, as shown on the right. The figures show the maximum curvature gain of 0.2, but the same applies to 0.4. There are 2 hypotheses that we developed for this experiment. One is that the discomfort perceived by users can be reduced by using dynamic curvature gain, and the other is that the larger the maximum curvature gain applied, the greater the discomfort while walking. This figure shows the results of the discomfort scores for each condition answered by the users. As there was a significant difference between the continuous and abrupt conditions, the continuous condition resulted in significantly less discomfort. In the same way, there was a significant difference between the 2 conditions of the maximum curvature gain to be applied, indicating that the smaller the value of this gain, the significantly smaller the discomfort. This result shows that the proposed method using dynamic curvature gain can reduce the discomfort by 9% compared to the existing method using only constant curvature gain. Therefore, the hypothesis that the dynamic curvature gain with continuous curvature change can reduce the discomfort is supported. And similarly, the hypothesis that the larger the maximum curvature gain applied, the greater the discomfort was supported. Finally, we explain the conclusion of this study. We proposed a method to apply dynamic gain with continuous curvature change in curvature manipulation to realize a more versatile and effective RDW. And experimental results show that the proposed method reduces the discomfort of curvature gain application by 9%. Although the explanation was omitted due to time constraint, it was possible to reduce the discomfort by 16% when bending gain was applied. This suggests that the proposed method can be used to achieve greater manipulation of the RDW than conventional methods. That is all. Thank you very much for your attention.
Okay, so thank you, Hiraki, for this really nice presentation. So I remember that you can use the Q&A from Zoom to post questions or Discord. So I will have first a question is regarding so in your experiment you have like these predefined trajectories. So you could apply your approach when there is no trajectory known beforehand. So the user is freely exploring the environment.
So the question is about how to apply dynamic gains.
So the user is freely walking and it's turning and it's doing like not straight trajectory, not a trajectory with a fixed curvature. So you can adapt your method to provide an adaptation of the curvature gain based on what the user is doing without knowing what he's doing. I mean, or beforehand and without any prediction of what he will.
The previous study used the constant curvature gain. So like the radius of real space is constant value, like 22 meters. And so maps the user's position to arc trajectory to straight line trajectory. So, but in this, our proposed method, in the real space, the users walk along a coscoid curve. So this is this changes the radius continuously. Like so, at first the radius is infinite or very big value. So the user, so if the user walks along the path, so the radius is gradually small, like so 100 meter, 50, 100 meter to 10, 100 meter, 100 meter to 50 meter to 20 meter to 10 meter, like that. So the users can see the walking path and so walks on the path, so they can walk on the closed curve, and we can apply the dynamic gain. So we can apply dynamic curvature gain.
Okay. So maybe we can do just a last question from Xingxiao Yu. So they said that for continuous and abrupt curvature, the users walk different distances before the redirected algorithm was applied. And it says that, do you think the distance they walked before the method was applied made any difference, or had an impact on the results?
So you mean the distance users walk is have influence on the discomfort, like that?
Yeah, it seems that the user had some and beginning of the trial there was no bending, there was no curvature applied.
Yes.
So do you think that this might have an impact on what happened next, or?
Yes. So this experiment, at first 5 meter, we apply no gain, and next 10 meter we apply dynamic curvature, dynamic gain, and the last 5 meter we apply constant curvature gain. So yes, so at first 5 meter users feel no discomfort, but next 10 meter, and so gradually we increase the gain, or we increase the amount of manipulation, so gradually. But so compared to the method of discretely increase the amount of manipulation. So the method to gradually increase the amount of manipulation can reduce the discomfort, because the users can adapt to the change of this gain change.
Okay, perfect. Thank you. So I think we will leave it here. So again, so you could continue the discussion in the Q&A in GatherTown or on Discord. Okay, so next speaker would be Zheyin Chen from the University of Beihang, China. And he will be presenting the paper entitled A Reinforced Learning Approach to Redirected Walking with Passive Haptics. So,
okay.
Zheyin,
Hello.
if you are ready, yeah, we hear you. So you can share your slides, please.
Okay. Can you hear the slides? Can you see the slides? Is that okay?
Yes, it's okay.
Okay, I will start the presentation. Hello, everyone. I'm Zheyin Chen from Beihang University, and I will give the presentation about our paper, a reinforcement learning approach to redirected walking with passive haptic feedback. VR applications are becoming more and more widespread, and users hope to be able to freely explore virtual spaces in a limited real space. However, when the size of the virtual space is much larger than the real space, the physical movement is often restricted. As shown in the picture, when the user wants to walk to the target point in the virtual space, it will be restricted by the boundary of the physical space and collide. Limited by this, we can use the reset operation. However, frequent reset operations will reduce the user's experience. So people propose the concept of redirected walking to alleviate this problem. To reduce collisions with obstacles, the redirected walking technology provides a series of manipulations to guide the user far away from the boundary when walking in the physical space. Users can explore a large virtual space even if they are in a small real space. Passive haptic is one of the important topics in virtual roaming. When the user interacts with objects in the virtual space during exploring, the corresponding feedback should be obtained from the real world. Experiments have shown that passive haptic feedback can significantly enhance the user's immersive experience. RDW technology is usually achieved through 3 gains. Translation gain is used to scale the user's translation in virtual space, making the user go further or closer, while the curvature gain makes user go in a curve with certain radius. The rotation gain is defined by the quotient of the rotated angle in virtual world and the real world. Excessive gains can lead to drastic changes in the virtual scene, which makes it perceived by users, and it will also bring dizziness and physical discomfort to the user. Therefore, the gains are limited to a set of thresholds. Steinecke experimentally measured a set of generally accepted threshold values for translation and rotation gain. For curvature gain, 7.5 meters is a commonly accepted threshold. So far, many RDW approaches have been proposed. Steer to center guides the user towards the center of the scene at all times, while steer to orbit guides the user to walk along a fixed arc. APF constructs an artificial potential field to steer the user far away from the obstacles, and the steer to optimal target is trained by reinforcement learning to locate an optimal heading direction in each moment. There are also a series of studies on the passive haptic problem. The approach UPH divides the walking process into boundary avoidance states and passive haptic states based on whether the user's heading direction intersects with the object. However, because it's not always in passive haptic state, it cannot guarantee the relative positions of the user and the target in virtual and real space. The reactive alignment with RDW extends the APF by adding an attractive component to pull the user towards the target. This method does not work well when the initial state is too far from the alignment state. Based on the existing method, This paper proposes a reinforcement learning-based redirected walking method with passive haptic. The first part is a process to generate the dataset. The second part gives the reinforcement learning-based training framework, including the description of state, input, output, and network architecture, as well as the design of a reward function. The last part is about the simulation experiment. The core of reinforcement learning is to let a virtual agent learn the optimal policy through trial and error. First, we input the current state ST into the multilayer perceptron to obtain the current action AT, while the multilayer perceptron predicts the corresponding expected return VST based on the current state. The agent gets the next state ST+1 after executing according to the action AT, and calculates the reward RT according to the reward function. Finally, we calculate the difference between the expected returns and the cumulative reward as a loss function. We update the MLP network using this loss function. After that, new actions can be made with the new multilayer perceptron, and the above process is repeated to allow the agent to learn while interacting with the environment. To train our data network, we need a large number of random walking paths starting from the virtual scene boundary to the target as the training data. First, we place the agent at the location of the target object, and we randomly initialize its direction. Agent walks in the scene according to certain rules. And at each timestamp, we record the horizontal and vertical coordinates and the heading direction. The process is stopped until the agent reaches one of the boundaries. By reversing the order of the values recorded during the walking, a target path is obtained from the boundary to the target. The state at each moment is a 6-dimensional vector consisting of the horizontal vertical coordinates and the heading direction of the corresponding agent in real and virtual space. In order to obtain continuous temporal information, 10 consecutive states are concatenated together to form a 60-dimensional vector as the input to the multilayer perceptron. The output consists of 2 parts. First is 3 pairs of value corresponding to the mean and standard deviation of the 3 gains. The other part is the expected return of the current state. The actions made by the agent are obtained by sampling the 3 gains using a normal distribution with corresponding mean and standard deviation. The core of reinforcement learning is the design of reward functions. The reward function for this experiment is consisted of 3 parts, which is the boundary avoidance reward, the distance deviation penalty, and the orientation deviation penalty. The weight factors of the 3 rewards are also adaptively adjusted according to the change of the agent's relative location in the scene. Boundary avoidance reward was first proposed by Strauss. It is calculated by 2 parts. First is the distance from the user to the boundary in heading direction. Another is the minimal distance from the user to the boundary in 2 directions perpendicular to the heading direction. This reward encourages the agent to move toward more open areas, thus reducing the number of resets. The left image shows a good state, while the right one is a bad state. Distance deviation penalty is designed to alleviate the inconsistency of the distance between the agent and the target in virtual space and real space. It's calculated by the difference between agent and the target distance in 2 scenarios. Orientation deviation penalty considers the working orientation of the agent relative to the target object. In virtual scene, let psi define the direction from the user's position to the agent object's position in the virtual space, and phi is the heading direction. Theta represents the side angle from psi to phi. It's similarly defined in the physical space. Compared with the distance deviation penalty, the orientation deviation penalty is more important because the working direction determines future path trajectories. We dynamically adjust the weights of the 3 rewards and penalties according to the relative position of agent in the scene. The boundary avoidance reward is inversely proportional to the distance of the agent from the real space boundary, and the effect of this term decreases when the agent is far from the boundary. Similarly, as the target gets closer to the target in the virtual space, we should pay more attention to the distance deviation penalty term. Since the rotation deviation penalty term is most important for controlling the relative position of the agent in two scenarios, its coefficient stays constant. We have done a large number of simulation experiments to verify the effectiveness of our method. The simulation data is generated just like the training set. For each simulation path, we configure the corresponding scenario settings as well as the agent settings. In each scenario, we compare our method with NAN, UPH, and REA3 algorithms. This experiment tests the performance of different algorithms in a variety of different virtual and real scenarios. The simulation test include real and virtual square and rectangular things of different sizes. The performance of the algorithm was also tested when the target was located on or off the center in real and virtual space. Under each space, we tested 5,000 simulation paths. Here gives the illustration of simulated virtual path under different scenarios. After the simulation scenario is configured, the agent is placed at any boundary of the real space, simulated the agent by following the virtual simulation path, and we stop the simulation until it reaches the boundary of the real scene or the simulation path ends. There are two metrics for these experiments. The first is NOC, which counts the number of collisions between the agent and the real scene. Boundary for each algorithm and scenario. And the second metric is the physical distance error. It measures the remaining physical distance between the agent and the target object once the agent reaches the target object's location in the virtual space. The experimental results show that reinforcement learning-based RDW algorithm can reduce the number of collisions during simulation tests compared with other algorithms. And in different shapes and sizes of spaces, the physical distance error can be reduced within a more acceptable range using our algorithm compared with others. To conclude, it is the first reinforcement learning-based method that addresses the passive haptic feedback problem in RDW. And we propose a new dataset generation method by reversing the path records. We have conducted quantitative experiments under various virtual and physical space conditions and verified that our method has significant advantages in both NOC and PDE metrics compared with other algorithms. Furthermore, the small architecture network can make this method computationally efficient to be used in real-time applications. Although various experimental results demonstrated the good performance of the proposed reinforcement learning-based approach, it has limitations that reveal the future research directions. First, the working behavior of simulated path and real human working path can be different. The creation of a dataset that consists of various real working paths is an ideal solution. Then our approach is based on an assumption that there is only one single target object in the virtual space for interaction. However, it may be expected to interact with multiple target objects in the virtual space, and we hope we can improve the approach to handle such situations. Finally, object direction was not considered in our experiments, which means that the user touches the virtual object equally from any direction. Proposing a more comprehensive reinforcement learning-based method to simultaneously optimize the distance error and the incident angle error between virtual and physical space is a promising future research direction. Thanks for watching.
Okay, so thank you very much, Sejin, for this clear presentation. So you can use the Q&A from Zoom and Discord for posing questions. So I have one question myself. So most of the parameters of your cost function takes into account the relationship between the user and, let's say, the tracking area and the object. However, in this case, you mainly kind of characterize this relationship between the user and the space. Have you considered other cost functions which might add other constraints regarding the smoothness of the gains applied, and somehow to abide, because I don't know what your simulation, if they generate like a smooth gain values, or there is changes along the entire path. So can you comment on this? I don't know if it's clear. I can make it simple. So I think if you consider other elements, your cost function, for example, more related to the user comfort while using the system, for example.
You mean why I choose to use the reinforcement learning to solve this question?
No. I mean the approach. I think I'm totally fine with the approach. Is that you have because I think that all the parameters of your cost function relates to the relationship between the user and the environment.
Yes.
There are other, for example, penalizations can be applied if there is a lot of jerkiness in the gains computed, or that, for example, that you generate some gains that go beyond the perceptual thresholds, for example. If I see what you mean.
You mean the parameters of each space? Is this the question?
Yeah, I mean, if you consider other elements in your cost function apart from these relationships between the user and the real world.
Oh yes, we just configure several situations that to prove this algorithm.
Okay. Okay, no problem. It's fine. So let's see if there is any other question. I have still another one. I guess, but this is, maybe this is future. Have you tried to use your system with real users, or it's something that you are planning to do?
Yes, because in this paper we haven't done the live user simulation test, and we just conduct the simulation test, and in the future direction we may create the dataset that consists of the real working dataset, and we perform the algorithm in the Unity to make it suitable for the real user test.
Okay, thank you. So again, so we can continue discussion in Gathered Town. So now we will go back to presentation number 1. So because we will play the pre-recorded video, so you can play it. So
hello everyone, I'm Yi Junli from Beihai University. Today I'll introduce our paper, OpenRDW, a redirected working library and benchmark with multi-user learning based on functionalities and state-of-the-art algorithms. Nowadays, with the increasing popularity of virtual reality applications, more people are willing to experience VR in room-scale spaces. When experiencing this immersive exploration, free movements in virtual environments are essential. However, traveling in the large virtual space can be highly constrained by the limited physical tracking space. Therefore, some effective locomotion techniques such as teleportation, walking in place, and redirected working were proposed to offer better VR experience. Among these techniques, RDW can provide a high natural feeling of working by introducing imperceptible manipulations to guide the user away from the physical boundaries, which enables users to explore a larger virtual space. For example, when a user plans to walk along a straight path in the virtual environment, the virtual camera could be slightly rotated so that the user unknowingly compensates this rotation by walking along an arc in the real world. This virtual rotation speed is usually controlled by parameters called gains. A taxonomy of redirection involves 3 major gains, namely translation, rotation, and curvature gains. To mimic the natural working process in the real world, the gains should be constrained within certain detection thresholds measured by user studies. Redirection controllers are specific algorithms which determine how gains are applied to steer users. Subtle redirection controllers steer users imperceptibly, including steer to center, controllers based on artificial potential fields, or reinforcement learning. but sometimes it is still possible for users to reach physical boundaries, which should be corrected by overt redirection controllers like Toolkit. To reduce the complexity of deploying RDW for VR developers, software libraries such as the Redirection Working Toolkit were developed to offer basic program interfaces for algorithm design, working simulation, and data logging. But till now, there are still very few released open-source RDW platforms, and more new features can be supplemented to handle complex application scenarios. In this work, we present OpenRDW, an open-source library and benchmark for developing, deploying, and evaluating RDW methods. OpenRDW contains two parts, the library and benchmark. The library offers hierarchical classes, so users can highly customize the RDW controllers. It's also convenient to do experiments and visualize the working process. Statistic results will be automatically exported. The library also supports reinforcement learning-based methods. The benchmark includes multiple testing conditions such as diversified tracking spaces, working paths, and RDW techniques. We implemented the OpenRDW library as a Unity 3D package for prevalent use in academia and industry. The architecture contains several basic modules and components. The movement component reads data from an input device or a predefined path to drive its avatar. Predefined paths are mainly used for automatic simulations, and these virtual paths can come from procedural generation and real-use working experiments. Redirection component receives the information of virtual scene and avatar movement to compute gains in real time. This component contains multiple candidate redirection controllers and determines which will be used according to the situation. For example, if the user is around the obstacles or boundaries, resetting controllers will be invoked to avoid collisions. Otherwise, subtle redirection controllers will be called for imperceptible manipulations. Our redirection component also offers support for reinforcement learning methods. We also implemented the state-of-the-art reinforcement learning method as a built-in example. The global configuration module defines data structures to store gain thresholds, tracking space, and other parameters. This module also controls the beginning and the end of an experiment. An automatic simulation can be executed in two modes. In the standard mode, the simulation process is rendered and displayed at the target frame rate, which helps researchers to observe the simulation clearly. In the backstage mode, the rendering pipeline is omitted to accelerate the simulation process, which is useful for fast batch testing. The tracking space component defines the data structure of the physical tracking space. There are two predefined types of tracking space: size-varied tracking spaces and shape-varied tracking spaces. Users can also customize the tracking spaces for testing. The visualization module visualizes the working process. There are two modes for visualization. In overview mode, the top view of the whole tracking space will be shown. Redirected paths of different avatars are highlighted in corresponding colors. In following mode, a user-specified virtual avatar will be followed. The target working paths and redirected paths are highlighted in blue and red respectively, and paths of other avatars are temporarily hidden. In order to analyze the performances of RDW methods under different conditions, diverse information and metrics are recorded by the analysis module. This module also supports high-quality exportation of the simulation process videos and working trajectory images. To support multiple real-use working, OpenRDW library integrates Photon Unity Line Working tool for network connection and synchronization. This video demo shows two HTC Vive users working in the 6 meters by 6 meters physical tracking space. A 1 meter by 1 meter square obstacle was set in the middle. Based on the library, we constructed a benchmark to evaluate RDW methods while simulations. There are two types of tracking spaces in our dataset. The first type is size-varying tracking spaces. Each space is in square shape and 4 types of side lengths are used. The second type is shape-varying tracking spaces, aiming to test the scalability of RDW algorithms in complex application scenarios. In our dataset, 6 varied shapes with 3 obstacle settings are designed. To make the testing data diverse, the virtual paths are obtained via procedural generation and real user working. There are 6 types of procedurally generated paths. Among them, random turn and 90-degree turn are generated randomly. Other paths are generated following certain patterns. We also collected paths worked by real users. These paths are more diverse because each user's working data could be different in both trajectory and working speed. There were 2 tasks. The first task was a waypoint collection in a simple virtual scene. Participants were asked to follow the procedurally generated green spheres. The second task was prop searching in 2 virtual scenes. The positions of virtual props are marked with stars showing on the right figures. The office scene contains 10 trophies, and the store scene contains 10 sandwiches for participants' collection. The participants were asked to collect all of the virtual props by searching and reaching them using Vibe controllers at their normal working speed. Currently, this benchmark integrated 10 RDW controllers. The method H2C and H2O represent the classic reactive controllers. Zigzag represents the classic predictive controller, which can fold a sawtooth-shaped virtual path into a back and forth pattern. Besides, there are 4 APF-based methods to represent the state-of-the-art reactive controllers, and steer-by reinforcement learning represents the state-of-the-art predictive controller. Regarding resetting controllers, 2-1 turn is the most common resetting strategy. While the APF resetting makes the user physically rotate towards a vector calculated by artificial potential fields. OpenRDW benchmark contains a variety of combined conditions of tracking spaces, virtual paths, and the number of users for adequate evaluations. Here we show a few representative results. All baseline methods can use 2-1 turn as the default resetting controller. Additionally, APF-based controllers can combine with the APF resetting controller as alternatives, which are denoted with an asterisk. For size-varied tracking spaces, results of resets and distance between resets are shown in the figure. For shape-varied tracking spaces, we only evaluated 8 combinations due to the scalability issues of applying some of the controllers. One visualization example of the same virtual path redirected by 3 methods is shown on the right. For multi-user working, results of resets and steering rate of curvature gain are shown in the figure. For more details and statistic results, please refer to our paper and supplementary materials. To conclude, we proposed OpenRDW, which is an open source library and benchmark for faster development, deployment, and evaluation of RDW techniques. It is beneficial to the whole community and supports both commercial and academic use. It also supports novel features like multi-user simulation and state-of-the-art methods. In the future, we will test OpenRDW on more VR devices. It is also worthwhile to compare different approaches with user studies. Moreover, we will improve the UI, simplify the deployment procedure, and integrate more state-of-the-art RDW methods. Because OpenRDW is a growing project, we will keep adding new features and welcome researchers to contribute to this project together. Thanks for watching.
Okay, so thank you very much, Yun. Although it was not, you did half of the presentation live, but we did that to make sure that everything was going good. So yeah, I guess that one of the answers was one of the questions was where we can download this interesting library, and I think you provided this link. I guess the link is on the is accessible in the paper. Can you confirm this? So if anyone wants to try this out.
Yes, we have just upload our project to the GitHub. I think if you want to download our project, now you can go to the GitHub by using the link in the last page of our slides.
Okay, so I would suggest that you put this link on Discord, because I guess there might be some people in the audience willing to have a look. And then I will have some questions regarding what are your plans for this library. So you plan to keep it improving it? You are thinking about adding more features? So what are your plans on this?
Yeah. Now we just integrate to some basic functions, and in the future, like what said in the slides, we will keep adding more new RDW algorithms and simplify the usage of APIs, and I think most of the future work is about the UI design and the usability. I think that's our future work.
Okay, so thank you. So again, if you want to continue the discussion and you want to discuss with Jijun about this interesting system, please contact him by GatherTown or in Discord. So let's go to our fourth presentation. So we'll be presented by Keigo Matsumoto from the University of Tokyo. And he will talk about galvanic vestibular stimulation, really exciting topic. So the floor is for you, Keigo. So go ahead.
So can you see me and can you hear me?
Yeah, it's good.
Great. Okay, so good morning, everyone. I'm Keigo Matsumoto from the University of Tokyo. So we propose a novel redirected walking technique using noisy galvanic vestibular stimulation, reduces the reliability of vestibular sensation, and increases the effect of curvature gain. To begin with, let's address redirected walking. So redirected walking can compress a virtual environment into a real narrow space. So most redirected walking techniques manipulate users' position and orientation through modified visual feedback of the virtual environment. However, the amount of redirected walking manipulation is limited that can be performed without the users being aware of the manipulation. According to the previous research, to apply curvature gain without the users noticing, it is necessary to have the user walking a path with a radius 6 meters or more. So moving on. Okay, so to increase the effect of redirected walking, researchers propose several approaches. One of the methods is using visual and auditory distractors, not to let users noticing redirected walking manipulation. Next, another method is adding other sensory stimuli to increase the effect of redirected walking, such as auditory and haptic cues. However, these methods restrict the content and virtual experiment. So how can we improve the effectiveness of redirected walking without any restrictions? So let's consider why we notice the manipulation of redirected walking in the first place. Our self-motion perception is composed of visual, vestibular, auditory, and proprioceptions. And during the redirected walking manipulation, visual and auditory stimuli come from the virtual environment, the head-mount display, while vestibular and proprioceptive stimuli come from the real space. So the inconsistency of these stimuli makes the user aware of the redirected manipulation. Therefore, to prevent users from noticing the redirected walking manipulation, it is effective to reduce the inconsistency between senses. Then, how can we reduce inconsistencies between these senses? According to the perceptual integration model, the probability distribution of integrated perception approaches that of the target sense by reducing the reliability of the contradictory sense. So in case of redirected walking, the probability distribution of the subjective coverage gain might be closer to that of the visual coverage gain by reducing the reliability of the vestibular or proprioceptive sensations. So we decided to use noisy ZBS as a method to reduce the reliability of vestibular stimulation. So ZBS is a method of presenting acceleration sensation by applying electrical current to the vestibular organs, whereas noisy ZBS is a technique used to treat vestibular disease, where the optimal current of noisy ZBS is used to improve vestibular sensory function by causing stochastic resonance phenomena. On the other hand, the previous studies show applying noisy ZBS above the perceptual threshold reduces vestibular sensory function. Therefore, we formulated the following hypothesis. Strong noisy ZBS reduces the reliability of vestibular sensation and increases the effectiveness of redirected walking. Here is an appearance and circuit diagram of our ZBS device. And the ZBS can specify the polarity of a current and the amount of current at an arbitrary update rate of 10 kHz. And here are the waveform and spectrum of the current we used. So we used white Gaussian noise for noisy ZBS. And this movie shows a user study. For each trial, participants walk towards the stand for 6.5 meters, while the curvature gain is applied for the last 5 meters. After the trial, a questionnaire appears and the participant answers using the controller. We conducted our user study in a two-way mix design. The between participant factor is amount of current for this one, while the within participant factor is a current condition, so with and without noisy ZBS. So two for current and with ZBS by 9 curvature conditions here and 8 trials. So the total number of trials are 144 trials. A total of 24 participants, 12 for each current conditions, completed the experiment. Here is the evaluation we conducted in our experiment. Due to the time constraints, I will show you only the result of 2 alternative false choice. So these are our working hypotheses. Working hypothesis 1 is optimal noisy ZBS decreases the effectiveness of redirected walking by increasing the reliability of vestibular sensation. And working hypothesis 2 is strong noisy ZBS increases the effectiveness of redirected walking by reducing the reliability of vestibular sensation. So we performed 2 analyses of 2 alternative false choice results. The first one is pooled detection threshold, which is estimated using the result of all participants. And the second one is individual detection threshold, which is estimated using the result of each participant. So here are the results of 2 alternative false choice in 0.3 milliampere current condition, so optimal noisy ZBS. In the noisy ZBS condition, the pooled detection threshold was at 0.0440 and in the control condition, it was at 0.378. Meanwhile, mean individual detection threshold in the noisy ZBS condition here was at 0.442, and in the control condition, it was at 0.415. So the results show that the pooled detection threshold of the noisy ZBS condition was numerically expanded, but no significant differences were found. Next, here are the results of two alternate force choice in 0.5 milliampere current condition. In the ZBS condition, the pooled DT was 0.372, and in the control condition, it was at 0.0332. Meanwhile, the individual detection threshold in the noisy ZBS condition was at 0.0314, and in the control condition, it was at 0.0337. So the results show that the pooled detection threshold of the noisy ZBS condition was also numerically expanded here, but no significant differences was found. So let's move on to the discussion. Although pooled detection thresholds suggest that the noisy ZBS expanded the detection threshold of curvature gain numerically, the comparison of individual DTs showed no significant differences. Therefore, working hypothesis 1 and 2 were not supported. And we also found that their detection thresholds varied considerably among individuals. Moreover, the same amount of noisy ZBS was applied. The detection threshold increases or decreases depending on the participant. So from the result, we think that the amount of current that improves the effect of redirected walking may differ from person to person. So our limitation has some limitations. So first, the number of participants in this experiment was relatively small, and the gender ratio was somewhat skewed. So these may affect our result. Also from a previous study, ZBS may have a residual effect influencing the result also. And in this study, we applied constant current values, but we should use the current value appropriate for each user in the future studies. So here are the conclusions. Thank you for listening, and I will be happy to answer any questions.
Okay, so thank you very much, Keigo, for this really exciting presentation. So let's go. We have a first question from the audience. So Xingjia Wu says a very impressive work. So I think he was a bit scared about this GPS. I was wondering about the ethical approval, but I checked that you had that in the paper. So so yeah, feel relief, Xingjia, that there was an ethical approval. But well, I guess that you might have some issues with this, but I guess should be okay once you talk about the safety of the system. In any case, I was really interested about this part. You're talking about this inter-user variability. So you say that you saw like there was a lot of variability between users. So this was extremely big. I mean, there were some people that did work really well and for people that didn't work at all. Yeah, how was it? So maybe just briefly you can comment on this.
So I told about so there's my pointer. Okay, so in some users, using a 0.3 milliampere current condition are very effective, but meanwhile, other users are not working at all, but 0.5 milliampere, so strong current condition is very effective. So I think because of the conductance of the skin or vestibular organs, the differences are very affect these individual differences. Okay.
Maybe I have also like just a curiosity question. How is this perceived by the user? So it feels some tingling in the area where the stimulation is going, or it's totally unperceivable? I mean, it's just the vestibular which has an impact.
Mm-hmm. So in the 0.3 milliampere conditions, almost all users have no sensation on their skin. And strong current condition, 0.5 milliampere is actually the threshold of perceptual current for skin, electrical skin. So some user noticing the electrical sensation, but others are not. So 50-50.
Okay. Okay, thank you very much, Keigo. So there is yet another question from Xingjiao, but maybe you could continue the discussion in Discord. I think it's a really
I will answer more details in the others.
So let's move to our fifth speaker. So let's see, we might have we might end a bit later than scheduled, but should be fine. So please, I will ask to Dangpeng Chen to please join us. So Dangpeng, are you there?
Wait a minute.
Yeah, okay, so please start sharing your slides.
Yeah. I will prepare.
Yeah, and Keigo, don't forget to mute yourself.
Sorry.
Oh, sorry.
No problem. Okay, so the next speaker is Dangpeng Chen, from a student from the Zhejiang University. And he's going to present RNINVEO, so robust neural inertial navigation aided visual inertia odometry in challenging scenes. So we have a paper which doesn't talk about redirected walking. So after please, Dangpeng, can you start sharing your slides, please? Or if not, we will go to the backup video if you are having some issues. So yeah, maybe I can ask Enrique Andrea, maybe if you can prepare just in case the video. So because maybe it seems that Dangpeng is having some issues. So for the sake of time, we can move to the. Okay, so we will go for the pre-recorded. Just to avoid, but please, Dangpeng, join us for the Q&A. Okay, so.
Hello, everyone. Welcome. We present RNINVEO, Robust Neural Inertial Navigation Aided Visual Inertial Odometry in Challenging Scenes. Motion tracking is a key technology for AR or VR. High precision and robust camera position tracking are required to improve the immersive experience. Visual inertial odometry can achieve high precision and robustness on a mobile platform using a camera and a low-cost IMU. At present, many excellent AR developer platforms in the industry have adopted similar visual inertial tracking solutions, such as Apple's ARKit, Google's ARCore. Although the existing visual inertial odometry has achieved state-of-the-art accuracy and stability, there are still many difficult problems in the application of consumer-level AR. The current visual inertial odometry always relies on continuous and reliable visual tracking, which always fails when the visual information is quite weak or confusing, such as the scenes with weak or repeated textures, occlusion, fast camera motion with serious motion blur, and so on. The purpose of our work is to make better use of IMU information to reduce the dependence of visual information in the VR system. The IMU measures the acceleration and angular velocity of the device movement, and the acceleration data must be integrated twice to get a prediction. However, consumer-grade IMU data contains various noises, such as white noise and bias, which will bring a significant error accumulation. Traditional methods use zero velocity update or step counting to reduce the cumulative error, but these methods only work well under periodic pedestrian motion. Data-driven based methods use windowed IMU measurement as neural network input to estimate relative displacement or velocity. The IMU-based odometry methods are low precision but environment independent. Inspired by these methods, we try to integrate the robust non-low prediction neural inertial network observations with the traditional visual inertial odometry to construct a highly robust and precise tracking system. The structure of the proposed system is illustrated in the figure. Our estimation system takes IMU data and image as input and is mainly composed of 4 modules, including preprocessing, initialization, neural network, and filter. This is our network architecture, which consists of the 1D version of ResNet 18, standard LSTM, and fully connected layers. We use the ResNet module to learn human motion hidden variables. However, we believe that human motion is continuous and regular, so we use LSTM to fuse the current hidden state with the previous hidden state to estimate the best current hidden state of motion. Finally, 2 fully connected layers are used to regress the relative prediction of the window and the corresponding covariance. At each time step, the network infers motion based on a hidden state and a local window of acceleration and angular velocity in the gravity-aligned inertial frame. The outputs are the relative displacement and their uncertainties. To make the network care about the local accuracy and also pay attention to the long-term global accuracy, we decide relative loss and absolute loss. The mean square error and negative log likelihood error are chosen to optimize the loss. Except for neural inertial network measurement, other modules of our fusion system are similar to traditional VIO. There are 2 important points that require attention here. First, the learned movement pattern is the yaw angle equivalent. That is, measurement changes with the change of the yaw angle at the initial window frame. Second, the network predicts time is not aligned in time with the estimated state. Therefore, to completely define the motion constraints, the propagation of IMU is needed. We conduct a series of experiments to verify the accuracy and generalization of our proposed neural inertial network and the accuracy and robustness of our fusion system. Figures shows the error distribution on the entire test set and the trajectories. It confirmed that compared with RONIN and TLIO, our system consistently maintains higher accuracy. The tables show that the IMU neural network can be generalized to different people, different devices, and different environments. Our end-to-end network can also achieve the best local and global accuracy. Our proposed network without absolute loss only achieved good local accuracy, but poor global accuracy. The tables show the accuracy of RNIN VIO is close to that of BVIO in normal scenarios. However, in challenging scenarios, the accuracy of RNIN VIO is significantly better than that of VIO. Here is a video demo of the comparison in challenging scenes between RNIN VIO with BVIO. In challenging scenarios, the NIN method has better robustness. The VIO algorithm fused with NIN has higher robustness and higher accuracy.
From the video, we can see that NIVIO had a little drift, but BVIO had a very large drift. Even in some challenging things, like some things like low texture, weak texture.
Our student volunteers, resulting in a total of 111 participants that are roughly split. We have with the males and the females. And
Ben, can you mute yourself?
And you can see from the map in the bottom right, for example, that these programs were able to touch individuals in 36 different countries.
This is an AR demo. It also shows the same conclusion.
This is an online AR video demo, which can compared with AR core, BVL, and RNNVL. And we can see that the RNNVL had a high precision, but others, such as AR core and the BVL, had a very large drift in this challenge scene.
Okay, so thank you very much. I'm sorry, Dangpeng. So we went for the safest option to pre-play the video. So, but so again, if you have any questions, please use the Q&A or Discord. So I'm not really an expert on this on tracking and so on. I was curious about how easy it is to use this system. So these algorithms in commodity hardware. So all the method you propose can be used in a mobile phone without any major problem, or there is any constraint?
You mean this algorithm? How to put this algorithm on the mobile platform?
Yeah, if there is any computer power limitation, or I mean, they can run in a commodity hardware without any problem.
There are two main parts of our system. The first part is the traditional VL system, and we use some very effective filter-based VL system, which had a very low CPU cost. And the other part is the narrow network, and we can see in our presentation the network is very simple, but can handle a large number of measurement, and the cost of the network is also very low. So both of the two parts have a low cost on CPU. So we can port the system on the mobile device. Yeah.
Okay, that's great. So thank you for the clarification. And again, so for the sake of time, we will move to the last presentation, but you can still use so got it down on Discord to ask the Dangpeng question. So please, Ziming, if you can start sharing your, or Zhulong, I don't know who's sharing. Okay. So in this last presentation will be two presenters, so Ximing Ye and Junglong Chen. Both they are coming from the Beihang University, and they are going to present the paper PAVAL, so position-aware virtual agent locomotion for assisted virtual reality navigation. So the floor is for you. So please. We don't hear you. Are you there, Junglong? Or so we see the slide, but we don't hear you. Please tell us if you are able to do the presentation. If not, we will have to switch to the backup video. I think we see the slides, but we don't hear you. So yeah. So Eric, Andrea, maybe if you can, maybe we will go to the, because we are already running too late. We don't hear you, Julong. Okay, so, yeah, so please, Enrique, Andrea, could you start sharing the video? Yeah, thank you for all your help with this. Yeah.
Hello, and welcome to our presentation on Pavel, Position-Aware Virtual Agent Locomotion for Assisted Virtual Reality Navigation. My name is Junlong Chen, and this work is completed with Ziming Ye, Miao Wang, and Yongliang Yang. Let me begin with a brief introduction of the background of virtual agents. Virtual agents are typical assistance tools for navigation and interaction in VR tour, training, education, etc. Our work concerns virtual guides. Similar to guides in the real world, virtual guides serve as both a good pathfinder, which leads the audience through an unfamiliar environment, and a good mentor, which provides information to the audience. It has been demonstrated that the gaits, gestures, gazes, and positions of virtual agents are major factors that affect the user's perception and experience. Here, gaits, gestures, and gazes are beyond the scope of our paper, and we choose to study the positioning of virtual agents specifically. The goal of virtual agent positioning is to determine the position and orientation of the virtual agent, given the virtual environment and the current position of the user. There have been previous works regarding the positioning of virtual agents. Lang et al. Studied the positioning of virtual agents in mixed reality, where the user's position is fixed. Liang et al. Synthesized virtual pet behaviors in mixed reality, where the positioning of the virtual pet was achieved by understanding the scene context. In our design of the adaptive positioning technique, we refer to studies of spatial interaction of human guides with their audience. Best et al. Emphasized that interactions play a crucial role in guided tours. Kendon et al. Analyzed various kinds of socializing phenomena and concluded that there exist several interaction spatial formations, such as the L-shaped dyadic F formation, the vis-a-vis F formation, the horseshoe formation, clusters, and common focus gatherings. It is important to note that their findings provide insight into the design of virtual agents in our study, where the position and orientation of virtual agents are based on the aforementioned interaction spatial formations. Our motivation for proposing a new adaptive positioning algorithm for virtual guides was that most of the current virtual guides had the following three shortcomings. Some of them had a fixed position and orientation, and didn't consider the semantic information of virtual scenes. Some of the virtual guides didn't pay due attention to the user's experience and blocked the user's view. Some of the virtual guide positioning algorithms require tuning if a new virtual environment is adopted, and couldn't calculate the virtual guide's position in real time for a new virtual environment. Based on the shortcomings of current virtual agent positioning techniques, we propose the following design guidelines. Number 1. User-centric. The user should be able to explore the virtual environment as they wish, while the virtual agent only assists the navigation as the guide. The design of the virtual agent should take the user's overall experience as its main consideration. Number 2. Position first, then orientation. First of all, the virtual agent should be aware of the positions of the user, as well as information of the virtual scene. Furthermore, the virtual agent determines its position with a higher priority than setting up its orientation. Number 3. Natural locomotion. The locomotion timing and trajectory are expected to be proper and natural. Moreover, the virtual agent should have natural gestures and expressions, and avoid any unnecessary movement to prevent distraction. Based on the design principles, our framework can be divided into the following 4 steps: determination of object of interest, optimization of virtual agent's position, optimization of virtual agent's orientation, and from positioning to locomotion. Now I will introduce these 4 steps respectively in greater detail. The first step is the determination of the object of interest. We consider a virtual object as a candidate object of interest if the object is within a 3-meter range from the user. By giving the user's current position, the object of interest is determined as the one close to and oriented towards the user as much as possible from all candidates. The feasibility score is used to evaluate the selection of object using the following formula, which consists of a position term and orientation term for the candidate object of interest. After finding the object of interest, the next step is to optimize the virtual agent's position. We first conducted a preliminary user study on optimal virtual agent position and orientation with fixed user position. Each participant stood at fixed positions of 1 meter, 1.5 meters, 2 meters, 2.5 meters, and 3 meters away from the statue, and was asked to set up the male virtual agent's optimal position and orientation. To represent positions, we set up a Cartesian coordinate system as shown. We also use a polar coordinate system to represent orientations. We invited 18 participants and altogether gathered 360 data points. The left figure shows the virtual agent positions chosen by participants at different distances from the target statue. To rule out the possibility of asymmetric results, we fitted the functions of z with respect to distance d and x with respect to distance d for the left and right side respectively. We found that the virtual agent's position can be formulated as quadratic functions x of d and z of d with respect to the distance d. We plug in the optimal positions for the virtual agent into the above equation, which penalizes any deviation from the optimal position. This can be regarded as the score for the virtual agent's position, EP, where sigma is a constant parameter 1. PTA is the virtual agent's position, and P hat is the optimal position. Intuitively, this score function is maximized when the virtual agent's position is identical to the optimal position on the left or right-hand side. The optimal positions are calculated using the previously mentioned quadratic fitting functions. For the right figure, the position score is plotted, and we can see visually that the two optimal positions are on the left and right-hand side. Since the virtual agent needs to perform natural locomotion based on varied user positions, we add a soft constraint to avoid the virtual agent from moving at will and distracting the user's attention via a score for the virtual agent's locomotion, EL. When the virtual agent does not move from time t-1 to t, the score is largest. Hence, this term encourages the virtual agent to stay at the previous position, or to move as little as possible. Combining the effects of EP and EL, we get the position score distribution on the right figure, which tells us that the virtual agent should move to the optimal position on the user's left-hand side instead of the user's right-hand side, and is hence more reasonable. After optimizing the virtual agent's position, we move on to optimize the virtual agent's orientation. The optimal orientation is also determined by fitting data from our preliminary user study. In the left figure, the corresponding orientation for each virtual agent position is represented using a color wheel. Here, we formulate a polynomial function theta with respect to the virtual agent's position xz to fit the orientation data. In the fitting function, omega 1 to 6 are constant coefficients for the polynomial. After fitting, we can visualize this orientation fitting function for the user's left and right-hand sides respectively, as is shown in the right figure. Our next and final step is to find a locomotion path for the virtual agent to get to the optimal position. This is accomplished by connecting the optimized positions and orientations using the A* algorithm integrated in the Unity navigation system. So far, we have finished our introduction of the 4 steps in our design framework. Now we move on to the evaluation of our virtual agent positioning method. For our baseline methods, we have chosen 2 techniques, FRT and FRU. Fixed relative to target, or FRT, means that the virtual agent position and orientations are fixed relative to the target. FRU, or fixed relative to user, means that they are fixed relative to the user. For our method, Position-Aware Virtual Agent Locomotion, or PAVL, the virtual agent positions and orientations are optimized and updated in real time. To evaluate our methods, we conducted another user study where 27 participants rated the 3 positioning methods based on 3 measures in 3 different virtual environments. Each participant compared 3 different virtual agent locomotion techniques by exploring the virtual environment with the free walk, until they were able to evaluate each method. Everyone experimented in 3 scenes in the Latin square order. To give you a more intuitive understanding of the 3 different methods, this video shows first-person views of the 3 virtual agent positioning methods in a museum virtual environment. Through this video, we can see the effects of the different position and orientation of the virtual guides. The participants rated based on these 3 measures: the static position, referring to the virtual agent's position when the user and agent are static; the dynamic position, referring to the virtual agent's position when the user and agent are moving; and the static orientation, referring to the virtual agent's orientation when the user and agent are static. This box plot shows the static position, dynamic position, and static orientation ratings for the 3 methods under different virtual environments. From the box plots, we can see that in terms of all 3 measures, Pavel outperformed the 2 baseline methods under all 3 virtual environments. Non-parametric tests for all groups of data also provide evidence for the statistical difference between the ratings of Pavel and FRT, as well as Pavel and FRU. In terms of position, Pavel achieved better results because FRT could cause the virtual agent to occlude key objects. For FRU, the constant presence of the virtual agent can distract the user. As for our method, Pavel computes the optimal position in real time, while considering the trade-off between occlusion and distraction. In terms of orientation, Pavel achieved better results because the 2 baseline methods have fixed orientations. Meanwhile, Pavel optimizes the virtual agent's orientation based on the current position and orientation of the user, as well as semantic information, making it more natural and realistic. To sum up, our work can be divided into 4 parts: proposal of new design guidelines, determination of new data-driven prediction models, devising a novel real-time algorithm, and conducting a user study to evaluate our method. We do acknowledge, however, that our technique does have limitations. First, the behavior of virtual agents is simplified and not fully interactive. Second, only virtual agent locomotion for single user navigation is considered. Third, neural networks can be alternative solutions to solve the regression problem. That would be the end of our presentation. Thank you for listening.
Okay, so let's thank the authors for this last presentation. So are your mic is working, Jumlong? Because if it's not working, it would be hard to do the Q&A. Okay. So let's, yeah, so if it's not working, maybe we might, so we see you, but I don't know if we hear you. No, we don't hear you. The audio is not working. Okay, so if not, for the sake of time, because we are really running late, so I will just ask to all the speakers to turn on their camera so we can close the session. So yeah, I would like again to thank all the speakers for their time and for effort for presenting and for being here, for their work, of course. And so again, as Enrique Andrea is remembering, so please join us in Gathertown so we could continue the discussion. And yeah, let's do a virtual applause to all our speakers. Thank you, everyone. Okay, so let's close the session. And thanks to all the student volunteers for helping us with all the logistics. Bye-bye, and enjoy the conference.
Bye-bye.
Bye-bye.